As we begin to talk about the idea of evolution, there is this very first statement on the screen here that I want you to focus in on. What evidence exists to support the idea that life has changed over time and that all life is related? There are two key words in that statement that I want you to always remember: change and related. That's really the idea of evolution. Have living things over the course of the entire history of their existence changed? And are they all related? That's the key thing, and you will hear me come back to that idea over and over again as we work our way through this unit. All life has changed, and life is related. In order to supply some sort of evidence of those two things, one of the obvious pieces of evidence that most people would think of would be that of fossils. As stated here, fossils can come in a couple of different versions. You can see molds and casts as described here. But probably one of the things that is going to add support to the idea of evolution when it comes to fossils would be able to know, well, how old are the fossils? One of the ways that that can be achieved is through something called relative dating. You can see the picture represented here on the right of the Earth's surface and then the layers of sediment that exist below the Earth's surface. The idea being that layers of sediment pile up on top of each other as time goes by. And so if you look at the different layers, if you would find a fossil, for instance, in this layer and a different fossil in this layer, well, the deeper the layer, the older that layer happens to be, and therefore the older the fossil is. So in terms of dating the fossils, can you actually put a year? This fossil is 10,000 years old, or this fossil is 100,000 years old? Well, not in this case of using relative dating. The idea being that this fossil is newer or younger relative to the fossil that would be found down in one of the layers further down. More accurately, however, there is another type of dating that can be used for fossils called radioactive isotope dating. This is a little bit more complicated than the relative dating. The idea being that there are isotopes of some elements that exist on the periodic table. All that means is that there are different forms. So, for example, the one that we're going to focus our time on is carbon. Although carbon is carbon, there are several different types. And listed here on the bottom left-hand corner would be carbon-12 and carbon-14. Those two numbers simply mean that carbon-12 weighs 12 AMUs, or atomic mass units, and carbon-14, of course, weighs 14. The reason they are different is because of what they're composed of. Now, all atoms are composed of protons, neutrons, and electrons, but it's the number of those things that is different. As we think about the weight of carbon-12 and the weight of carbon-14, of course, it's the protons, neutrons, and electrons that add up to compose that weight. The funny thing is that electrons, although impossible to actually weigh zero, are close enough to zero that we basically say that they contribute no weight to the weight of an atom. That leaves the protons and neutrons, which each weigh 1 AMU. So for instance, carbon-12 has 6 protons and 6 neutrons, therefore it weighs 12 AMUs, and carbon-14 also has 6 protons, but instead has 8 neutrons, and thus it weighs 14 AMUs. The difference in weight and the difference in the number of neutrons contributes to the fact that carbon-12 and carbon-14 have several different properties. Although they're both carbon and share many of the same properties, carbon-12, as stated on this page, is stable, meaning that carbon-12 will always be carbon-12. Carbon-12 today is going to be carbon-12 next week, next year, and 10,000 years from now. Carbon-14, on the other hand, goes through what is called radioactive decay. It is very unstable, and so it decays at a constant rate into a different element. The nice thing is that the rate at which it decays is consistent, and it is referred to, as stated here, as the half-life, the time it takes for half of the radioactive isotopes of an element to decay. So for instance, if we had 8,000 atoms of carbon-14 and we sat around and watched it for one half-life, there would only be 4,000 atoms left after that one half-life. The strange part is, if we sat around and watched those 4,000 for another half-life, there would only be 2,000 left. In other words, it would continue to divide itself in half, and then after that, 1,000. How long is a half-life? Well, according to this chart, and we look at carbon-14, it says the half-life is 5,700 years. We're going to be a little bit more accurate than that. We're going to use this number. 5,730 years is the half-life of carbon-14. The nice thing is that in living tissue, there is both carbon-12 and carbon-14, and it exists in all living tissue in the same basic ratio. And we can use that fact and this idea of half-life to figure out the age of a fossil through radioactive isotope dating. How are we going to do that? Now, here's a basic problem. Let's say here's our fossil. We find a fossil and we count up the atoms of carbon-12 and carbon-14 in that fossil, and we find 360,000 atoms of carbon-12 and only 7,500 of carbon-14. Now, how are we going to use that? As I said, there is a consistent ratio in living tissue of carbon-12 to carbon-14. Now, I know this is not the correct ratio, but it's the one that we're going to use in order to make the math a little bit simpler. We're going to say that in living tissue, there is a 3-to-1 ratio from carbon-12 to carbon-14, and therefore there would be such in a fossil as well. The problem, of course, is that a fossil is not living any longer, and therefore carbon-14 has been decaying. Carbon-12, on the other hand, has not. If there are 360,000 atoms of carbon-12 in the fossil, there were 360,000 atoms of carbon-12 in that living thing. So if we take that number and we apply this 3-to-1 ratio, we can figure out how much carbon-12 there was, how much carbon-14 there was when this living thing died. All we have to do is take 360,000, divide by 3, and we come up with 120,000. I realize I'm missing a zero there. I apologize. So there were 120,000 atoms of carbon-14 in this living thing when it died. But of course, when you found the fossil, there was only 7,500. So how many half-lives have happened in the meantime? So there was 120,000 divided in half once, twice, 3 times, 4 times. Hey, there it is, 7,500 matches the amount of carbon-14. And so to go from 120,000 down to 7,500, we divided those numbers in half 4 times. There's my 4. Each half-life is the same quantity of time. It's 5,730. So if we multiply 4 times 5,730, that fossil is 22,920 years old. One last little idea to go along with fossils here, although these aren't quite fossils. Instead of finding a fossil, a rock that is a preserved representation of a living thing, it is possible to find the actual living thing, still preserved. And we can do that in 3 basic ways. You can see in the pictures here on the left, we have amber. And amber is nothing more than hardened tree sap. And in this case, that tree sap formed around a living thing. So it's not really a fossil. It's not a rock of that, what looks like an insect. It's the actual preserved organism. In the middle here, we have an organism preserved in ice. And then on the far right, the idea that there are on Earth places where there are natural forming tar pits, and living things that died in those tar pits can be preserved as well.